Welcome to our seminar from the IAPS seminar series. Today we have Marzena Sniegowska from the Tel Aviv University, and his seminar is about the active galactic nuclei. I give the floor to Fiamma for the presentation of the speaker, and as usual, answers questions. I'm sorry, at the end of the talk for the people connected with Zoom. You can also write down your question in the chat. Thank you.
Good morning. I'm very glad to present today Marzena. Marzena is PhD in Copernicus Astronomical Center in Warsaw, under the supervision of Professor Marzena. She focused on theoretical explanation of changing look AGN. And now she has a postdoc in Tel Aviv University under the supervision of Professor Benny Yes, I'm sorry. And she is working on changing look AGN, but this time on the point of view of observational astronomy. So I left the floor to Marzena. Thank you.
Thank you very much. Hello, everyone. Yes, so I will start to, the title is a bit long, but so we will go through it. So first I will briefly explain what are active galactic nuclei, then what are changing look, active galactic nuclei, and what nuclear transients we may have there, and then how we can model them, and what are the challenges behind all of those models. Yes, so let's start with the motivation and in general what active galactic nuclei is. So we will be focusing on the unifying model. Maybe you saw it already on some seminars or during your studies. So we have the black hole, which is surrounded by accretion disk, which is accreting the matter and losing the angular momentum. And then this accretion disk, if we go to time scales, let's say, so this is more or less light days from the black hole. Then we go to a bit farther light days, I would say light months, to broadline region. In broadline region, we have broad lines created, and the farther we may have Taurus, which is responding in infrared to what is going on in the VLR. And then farther we may have narrow line region. And you know that the geometry of this is all under discussion, but briefly, like we know where are the radii, where the things are located. We may have jet, we may not have jet. I will be talking about non-jetted sources. And mostly we will be focusing on this seminar in this part. So we have accretion disk and broadline region. We will not talk much more further about Taurus or host. And from optical point of view, if we talk about flux changes in, let's say, normally well-behaved AGN, the light curve looks like that. So it's like not much is happening, just a bit of stochastic noise. That's what we would expect from AGN. And then if we take a look on optical spectra, we may see here O3 doublet, and this line is H beta. And depending on the viewing angle, so it depends if we see source from here. So we have Taurus, which is obscuring our broadline region. So then we only see narrow lines, like here. Or when we are from any angle from here, we may also see broadline region because Taurus is not obscuring our line of sight. We also see the broad component of line. And this H beta line is very important because we are estimating black hole masses using this line in the optical. Okay, so let's move on. Yes, so I was saying that if we see broad component or not, it depends only on the viewing angle, but there are some sources in which this H beta line, you can see here in 70, it was not here, then it appeared huge, because in O3, we always assume that it does not change, because it's really far from us, they're like, I don't know, timescale hundreds of years. So we can easily assume from observation to observation that this should stay more or less the same. So in comparison to this O3, you can see that H beta appeared and then disappeared again, which is a small tick there. And actually, recently I had pleasure to work with one student from Warsaw to re-observe exactly this source, which I was always showing in the introduction. And you can see here that the last year H beta reappeared again. So it's kind of, repetitive phenomenon that this H beta line is appearing, then disappearing. So then this challenging this unified model, because it cannot be from changing our viewing angle. Yeah, we are staying the same, the source stays the same, so it has to be something going on inside AGN, which we would like to understand what is going on there. And also, yes, why do we study those changing look AGN? Because yes, as I mentioned, they are challenged to this unified model, and many of them has been detected recently. I showed you one, but I think now there are more than 500, and we are really speeding up because now we will have this LSST, a lot of different surveys, and if we do then follow-up spectroscopy, we will probably easily go to thousands or more. So it will be nice to understand what are we working with. And also it will be nice to study it may help us to study coevolution supermassive black hole and the host, why some of them are showing this behavior, why some of them not. And yeah, we will probably better understand AGN physics, what is going around those black holes and accretion disks. So the first systematic search of those sources was done roughly 10 years ago by Chelsea MacLeod. And she used optical data from this PS 3Pi. And what they did, they were checking which sources changed in the photometry, the flux. And then for those sources, they were checking spectroscopy if the things changed. And here you can see that SDSS is this is archival spectrum. And you can see here this really nice, I will be calling it blue axis, really nice H beta line, and also the really big H alpha. And then in the BOSS spectrum, which was more or less 10 years later than from original SDSS1, which is from early 2000, there you can see that the shape of the BOSS, this black one, changed dramatically. We don't have anymore this blue part, and also it's quite difficult to see H beta line. And this behavior is calling to be turned on. We have turned on when we see the flare and the line appears, or turning off when the line disappears. And through the candidates, they rejected visually, and they found 10 unknown changing look. I'm saying now that we know more than 500, but we had to start from something. So that was the first search. And then there was another search using only archival data. So here what they did, they checked 2 optical surveys, publicly available, SDSS and LAMOS. And they were comparing in a very easy way. So they were checking if for the same source, they are getting in the catalogs the same classification. So their candidates for changing look were sources which were classified in one survey as galaxy and in another epoch from another survey as QSO or vice versa. And using this simple method, they found more than 20 new sources. So just in digging in the archive, we doubled the sample which was previously. And for now, the problem with this kind of search is that we don't know exactly the time scale. We have one spectrum done, another, but we exactly don't know when this change happened. It happened something between those dates. So maybe for now I was saying that, okay, time scales are 10 years, but maybe they are even months. It would be nice to do exactly follow-up once we are catching in the photometry that something is changing, which also then costs a lot. So it's another issue. And since then, there were many more systematic searches. including photometry. So as I said, like from the source, they were seeing that the source is going up. So then they were doing follow-up photometry and spectroscopy to check if the source is changing look. And using those methods, they found like more than 100 sources here, more than 60. And recently, with using the newest data from SDSS5, there are more than 100 newly discovered ones. And I think in the meantime also there was another by DESI. So I would say for now we have probably less than 1,000 sources, which is already quite a nice sample to do statistic on them. And so okay, we have already a huge sample. It would be nice to understand slowly what is causing those changes. So in the possible scenarios from the literature, I put them into two different classes, like extrinsic one or intrinsic. And extrinsic one, I think, is the most difficult to explain most of the sources, but not impossible. Now we will slowly go through all of them. So we will start from this variation of obscuration, which would cause, we have some kind of obscurer in our line of sight, which is hiding those broad lines from us. And then the question is, where exactly should it be located? How huge it should be to cover the whole broad line region? And also there were some studies using polarization in the optical, where they noticed that changing look, this was for the sample of 10 sources only, but for I think all of them, there was really low level of polarization. So it says there is no scatter, there is nothing which would obscure it. And also then if the obscurer would move, then the polarization should change. And also another problem with this explanation is let's multi-band recovery. So we see infrared responding to what is going on in the optical. So it means that it cannot start from the infrared. It's something closer to the black hole in most of those cases. But there was one source found by a PhD student from Tel Aviv University, where most probably that's variation of obscuration, because this is not flare. Here we have optical light curve from DPF, from two filters, so it's optical data. And you can see that here it's more or less stochastic, and then there was a dip, and then it came back to what it was in both filters. And if we check spectroscopy, the archival one is this blue one. So it was this turning off event, I would say, not the flaring one, but we have the dip, and then the lines will disappear. So we have our blue axis in the archival spectrum, really pretty H beta and H alpha line. H alpha is not disappearing completely because there is always a stellar component to it. So this line is not going completely to noise level. And then in 20 years later, those are two spectra taken during this dimming effect. And then they came back to what was observed before this dimming. And the challenges are that this time scale is only 2 months, and it has to be something to do with the obscuration probably. But for now, as I understand, it's not clear what was causing this particular source. But this source was so interesting to write one publication about just one source. Okay, we will go to another possible scenarios. Here I will be talking just about this canonical tidal disruption events. It means that when we have a star, it's coming too close to black hole, is getting spaghettified and disrupted, which causes the flare. And traditional TDE are happening in quiet galaxies. Then they are causing the flare, and it also affects the spectrum of the galaxy. But why not TDE in AGN? So in some cases, probably they could provide the answer. The problem is always with all of those scenarios with the time scales, because changing look are mostly like in the years for most of them. A typical TDE should be done in less than 1 year. And also then we have some sources in which we have repeated events, like the one I showed just at the beginning of the presentation. So then how statistically likely it is that we have repetitive TDE in all repetitive changing look AGN. And now on this I will focus the most because that's the part I've been working on. So changes in the accretion rate, it means that we have some changes in accretion disk flow, in accretion flow. And then this may be caused, the changes there may be caused by many processes. I'm working on radiation pressure one. In a meantime, in a while I will explain what it is. It can be some change in magnetic field. It can be changes of ionization, like similar to stellar ones. So we need some kind of process which would start this instability, and we have many of them, so that's possible. Then which of those instability would give us the expected time scales? We are talking about sources with 10 to 7 black hole mass, and we need tens, maybe a bit less than 10 years. So quite short time scale for evolution of those sources. And probably we will need some addition angular momentum loss, so maybe some winds, something extra to shrink the time scales. So first proposed model for those, it was, now we will go through this part that we have one source and one model, but also why all of changing look should have just one model. Maybe there are plenty of those possibilities. Maybe they also coexist, but this is too difficult right now to check. So for this source, Arcarian 1018, there are data in X-rays and in optical. So mostly I was talking in the optical, but now we will also take a look on XMM, I think, data. So with the time in this source, they noticed a dimming in so-called soft axis, and also those changes were accompanied by change in the optical. So here is our archival spectrum, and then you can see that the intensity of those emission lines disappeared, like dropped quite dramatically. And the proposed scenario for this source is that there is some ionization instability, which causes the flow, which was causing the soft axis, let's say, like mostly it may be warm corona, that it evaporated into this advection-dominated accretion flow. So this material, let's say, got evaporated there. But then if we would like to use this particular scenario for another sources, it's quite problematic because there was found already some example where there was no warm corona, which means there was nothing which was emitting from this part before the outburst. So not for all changing look, this particular scenario would work. Then there was another source and another interesting scenario to it. And here are just optical data. So we have SDSS archival data with this blue axis, H beta, H alpha line. Within time, this red spectrum is showing here very huge dimming. Even if we don't focus on emission lines, you can see this dimming here, which means that the matter got colder there. And then it came back to what it was. So somehow, most of those sources, if we observe, they have a tendency to come back to what was happening in them before. And here the explanation was that there was some kind of triggering effect which caused pulling front, which went outward the disk, and then it came back. Yeah, so we had pulling front which went outwards, so we had this case. Then when it came back, we got again what we had before the event. And here you can see a really nice example of how X-ray and optical astronomers can collaborate on the sources. There was one flaring AGN, and here there are two campaigns in the optical, which was started by Benny Trachenbrot, and the X-ray one, started by his colleague Claudio Ricci, and they were simultaneously observing in those both bands, in the optical UV and in X-rays, to check exactly what is happening there. And let's just for now focus on this photometry. So you can see that in the optical and UV we have dramatic flare and then slow decay. In the X-rays, it dropped. It dropped and then it came back maybe to what it was. And after this flare, they started also optical spectroscopic monitoring. And I hope you can see that here it's when the flare started. And H beta should be in this sequence. So here there's no H beta. It started to respond more or less here. From here you can see it. So after 3 months, broad emission lines started to appear, and for now they stayed there. So it shows that there was something intrinsic in the accretion disk causing the flare, and then from broad line region, which is more or less expected to be 3 months in a lifetime from the black hole, the lines answered to what was happening in the UV. And now there was another source and another possible explanation. Explanation proposed by Nicola Seppi, that maybe it was the reestablishment of magnetic flux. So when I was reading this paper, I was trying to imagine that it's something similar to what's going on in the sun, like we have the solar cycle. So here just you see the polarity of magnetic field change, and then they showed two possible scenarios, because this paper was before the event finished. So they were showing that it may come back to what it was, or a bit changed at the end. But this is the possible explanation of why this X-ray part was dropping and UV was, because it started from the UV, X-ray then reacted. There is one more possible scenario, but it was just like hypothesis and to show that it can be some other possibilities. That we may have close binary supermassive black holes, which may rotate around each other, and those mini disks may react depending on how they spin. So how the spectra would change depending on what case we have. But since then, there is no follow-up paper on that to check, for example, what light curves they could produce from this model. Now we will go to the model on which I've been working, and I promise there will be not equations, okay? We will just go slowly through assumptions and mostly what physically it's showing this model to us. So in my model, we are assuming quite simple Shakura-Sunyaev accretion disk with those assumptions, and we are solving two equations, differential equations. One on temperature, equatorial temperature of accretion disk, another on surface density. When we assume that they are equal to 0, we can get stationary solutions, which if we plot on this kind of, this is proportional to temperature. So this is more or less like log T, this is log sigma, which is surface density. We have 3 branches of the solution. This is called S-curve. And the one with the positive slope are where our solutions are stable, but we are interested in instabilities. So we need the one which is here, where the radiation pressure dominates. So from here, we will take our initial condition to run the code further. and starting more or less from here, so from radiation pressure. And then if we plot the light curve from it, we have some kind of like three phases of the outburst. So we have, we start from this, let's start from this black one, which is really huge increase of the flare, and then it's cooling down. And then mostly surface density is going up, temperature not that much, and it's like engine-like, more or less. And using this scenario, we were trying to compare just timescales to already observed changing look. So here we have our photometry for two sources, and you can see that they were observed for decades actually. And comparing for those, it's quite challenging, but that's the best what we have in the photometry. And you can see that maybe there are some kind of quasi-periodic changes of the flux. I will call it this way. So if we use these instabilities I mentioned, and we focus on a bit toy model, that we have our black hole here. We only compute things for this part, which is called unstable disk, like the box. We follow just this evolution. Farther we have stable disk, so there nothing is happening. Closer we have advection, and we are focusing only on this one. And we can shrink the time scales, just making this unstable zone more narrow. So then the outburst will be happening faster. And also we can, another parameter which we can change is where we exactly locate this unstable disk, how far from the black hole. And using this model, we produce some exemplary light curves just to check if we are getting timescales of roughly 10 years. That's it. We are not focusing on the shape of the outburst now, and also we are not producing any spectra yet. So here you can see many different light curves. You can see that they are quite sensitive. They change in how they look in the shape. We put them into 4 different m dot, which is accretion rate, different alpha, which is viscosity parameter, and what was the most interesting for us, how narrow or how broad this unstable zone is. And we may more or less succeeded to get more or less time scale. But we wanted to check a bit more realistic model, because of course it will be just not one box in accretion disk, it will be a bit more complex thing. Here is a comparison to our data, just to check if we are getting the timescales. And more or less with the timescales we are happy, but we wanted to check if we could get also the same shape of the outbursts. So we worked with Professor Agnieszka Janiuk from another institute in Warsaw. And instead of this simplistic model, we added this unstable disk zone. It was not just one box, but it was a lot of points. It was like grid of points calculated here. And if we just let this unstable disk, let's say, freely go, further, our timescales are thousands of years. So that's not exactly what we wanted. So we had to remember to cut this outer radius still strict. And just with this reduced outer radius, we were obtaining timescale less than 100 years, which is still not yet what we want. We added also hot corona to check if we can get those outbursts, let's say, more efficient and shrink the timescales. We did many different experiments, what is working the best, and what was working the best was just brute force, let's say, cutting this outer radius or adding magnetic field. So like when we don't know what to do, adding magnetic field may help sometimes. Here is briefly what we did in those experiments, but let's focus only on those plots. We were trying 2 different prescriptions for for magnetic fields. One was to add some extra energy transfer from accretion disk to corona to make this more efficient, or to not allow completely for this flow between accretion and corona. So then they would both immediately go towards the black hole. We were checking which one is more efficient. And I would say this model worked better. The ideas we took from the literature, actually, for both of them, just to recheck which one implied in our model would work better. And to focus on our results, for now, also just timescales. We still had this 3 phases cycle behavior, as I was showing a bit previously. The shape is a bit still problematic because we have those huge peaks. And for now, the timescales is it's still too big, but this is before adding magnetic field, just to show you how those outbursts look like if we just run the code. So we are plotting here one light curve for accretion disk, it's this gray one, and the other one, this dotted red one, it's for corona. So one is for accretion disk, another for corona, and corona is just passively following whatever accretion disk is doing. And when we add a magnetic field here, we can, let's just focus on those light curves for now. You can see that we can get different shapes depending on how strong this magnetic field is. So I was just experimenting with adding this part to equations to check when we will shrink the timescales, and here we have period versus how strong this magnetic field is. And at the beginning, I was quite worried because with the stronger magnetic field, you are getting even bigger periods. So that's not exactly what we wanted. But at the end, we were able to shrink it before putting the accretion disk in a fully stationary mode. Because with the too strong magnetic field, it was just, nothing was happening. It was just staying stable. But for some small part of this so-called magnetic coefficient, which was just extra cooling added to those equations, we were able to get tens of years. Okay, so this is one thing which we can do. We can add a magnetic field. Another, just to easily cut the outer radius, and that's the lower part. So if we start to cut in this brute force, it would mean that we have this unstable part, and then we have nothing. And then the question is how this nothing could be created. We may have maybe some, that's what we were explaining in the paper, that maybe there was some kind of tidal destruction event or something which went into accretion disk and opened the gap. So we have black hole, then this inner part, which we are modeling, then a bit of nothing, this gap zone, and then the rest of accretion disk. That then it could make it work, these instabilities with this outer, really small outer radius. And here you can see a lot of this fringing. It's because we have very close outer radius. So those waves are starting to interfere with each other. So that's why those funny shapes are appearing, not only those big flares like here, but also those extra ones. And if we go to other black hole related transients, I was talking about changing loop. When we have deep or increasing and our Balmer lines, H beta or H alpha, appearing or disappearing, we may have tidal destruction events when mostly they are happening in the quiet galaxy. We have huge flare, and then in the spectrum we have helium-2 appearing because the star is disrupted. So the Rembrandt of the star are showing in the spectrum. But recently, we observed few of really peculiar events in active galactic nuclei. So, for example, in this source, you can see this is archival spectrum, and we have here those Balmer lines. Broad lines, it means this is an AGN. and there was a really huge flare, then with some extra reflaring. And okay, we see here Palmer line, but we see here also those extra lines, which are not exactly the same as in TDE because their widths are smaller. And those lines are mostly created, they are created in vicinity of the black hole. So they are caused by some extreme UV flare, which is seen here. And that would actually maybe work with the model I showed. Because if we see here just examples of this very small outer radius, here it was just for exercise to see, because for 15 short side radius to go without adding GR, this is a very dangerous part. So, but if we focus on those two, let's say 30 or 50 short side radius, we see that we have those bumps, a bit higher bump, depends, with the time scales of more or less years. So we have some complex behavior in the optical, and this maybe would work for these peculiar sources I showed, because as I said, those extra lines are made in the vicinity of the black hole, flares in the UV optical part, and those light curves, they had quite rich structure. So here is another recurring flaring event which we found, and instead of this extra flare which was here, as in the previous slide, we have one flare, and then there is 4 years gap, and there is another flare, and during the decay there are some smaller bumps here as well, in the first flare and then also in the second, like here, for example, there is this extra bump. And here are a couple of spectra to show you. So here is also archival spectrum taken before all this happened. Here we have photometry from one instrument to show that there was nothing happening. It was just stochastic variability here, and then it happened. One dramatic event, the spectrum, this cyan spectrum was taken here. And that's very interesting that after first flare, nothing happened. But after the second, which is bigger flare, we again noticed this funny doublet here. So I am working currently on this source, and I hope within this month it will be on the archive. So going to conclusions. Yeah, many changing look have been detected recently. So it's really nice to have statistical sample to work on it, to test models, because we still have low level of the interpretation what's going on. It would be nice to get, for example, spectra models to compare with what is going on. We proposed one from the models, which is introducing radiation pressure instabilities. It would be nice to produce spectra at some point to show if at least the shape is behaved. And talking about this last funny sources, about this both broad, it's called Bowen lines, those two funny lines I showed you. That we know they are happening in AGN, but we don't know what is causing them. So that's still a mystery, and it would be nice to work on it, to solve it. Thank you.
Interesting talk about this important topic. We have a question.
Yes, thank you. A lot of questions and comments. I will select two.
Okay.
So the first is just a comment about this peculiar behavior you showed with the asymmetric broad lines together with UV bump with fluxes.
Sorry, those are extra slides. This one or the other source?
Well, yeah, this is okay, but okay. The other, I mean, it's okay. Also this one.
Oh, this one.
Yeah, this one. Yeah. And the central panel. So we know that this, I mean, we know an hypothesis about this asymmetric line could be due to, for example, the presence of binary supermassive black holes that are ionizing the touched broadline region, putting some modification is entroyed of the broad line. And if we believe to the geometry of mini disks around the two isolated massive black holes, I mean, I am echoing the geometry you were describing us about something nearby the black hole, a hole, and then something else. And I mean, it is a scenario that is often invoked as a binary supermassive black hole that really looks like the central plot you are showing, because there's the mini disk flaring, causing a huge UV emission and broad line and asymmetric broad line in the optical. I mean, this is just a comment.
Yes. Yeah, but then I think also you should see this asymmetry in the other lines, not only the one appearing here. Yes. But I don't know. It should be modeled. Yeah.
It depends on the time scale and the stage of binary phase you are looking at. So yeah.
Yeah, because they made many more spectra, but I don't remember if there was asymmetry. Maybe there was asymmetry. That's
one of the hypotheses that the asymmetry is very hard to check.
Yes, but yes.
Well, the question is about the optical versus X-rays you showed for the real change in look AGN, the easy one, let's say. And I'm wondering if, together with the photometry variability, you also were looking to spectroscopy. For example, in the case of X-rays, increasing in age with disappearing of the broad H beta could be caused by an increasing of nuclear absorption, so nearby the central part. If you see, for example, an extreme soft X part with appearing H beta, you may see that this looks like more to TD or something. Or maybe if you see the appearing or disappearing of the ion line, this could make one scenario better with respect to the other. So I'm wondering if, together with the nice light curve you showed us with optical and X-ray, you also consider spectroscopy on the X-ray?
Me personally not, because as you probably noticed during the talk, I am mostly optical, but I think Claudio Ricci, for example, is working on it, and I think it's important to not forget about X-rays, because then with optical we can be mislead with scenarios. With X-rays, we will have more proofs what's going on. But I personally don't work on X-rays.
I have a few curiosities. The first one is sociological. Why we are discovering this kind of objects only now, after decades of observations?
That's we were observing AGN, but we were observing them just once. It was like, okay, we saw we have spectrum, okay, done. But now we are,
It's like 4151 have been observed for 50 years now.
Yes, also this, 4151, 5548, but we had, I don't know, 5 of them only, with very detailed. If we did, detailed one for all AGN, probably we would already then know that it's not that peculiar. It's much more common than we thought, this phenomenon.
And following this question up, as a population, are there any correlations with whatever flux, spectroscopy, timescales, frequencies?
I think that, there is correlation with Eddington ratio. The lower Eddington ratio sources are doing it. So, for example, for narrow line Seifert, this changing look behavior will not rather be there. So where you have in the optical...
But in singles, individual sources, do you see switches corresponding to anything else? Flux or width of the lines or whatever?
Yeah, sometimes you see flares in AGN without changing the spectrum. And this, I don't know, I saw a few of them when we were observing, because we did, oh my God, huge flare, let's do a follow-up. And there is nothing in the spectroscopy, it looks the same. So I was not talking about them because those sources I understand even less. So, so maybe it would, I think for a few sources I have optical and X-rays, but in X-ray I didn't check from Swift photometry, but I didn't check what's going on there because I was like, okay, nothing in optical. So I put it.
No, I mean, the optical, just to comment on your question, the sociological one. The point is that, as you said, that we observe these typical AGN ones and say, let's see.
We have black hole mass.
Okay, but then we started to look for different spectra, but especially simultaneously with other parts. So we discovered that broad lines are when it is unabsorbed, narrow lines appear when it is absorbed. Then this check on different wavelengths doesn't appears probably recently,
yes.
10 years. But then the other sociological aspect is that now we tend to say changing look, even for sources that are simply variable. For example, 4151, in my view, it's variable, it's not changing look, just because we do not see this simultaneous changing in the optical and X-ray. While 10, 18 it is, or the other one, 55 it is.
Yes.
One last point, the limit cycle interpretation that you have been trying has been used also for galactic black holes.
Yes.
Have you tried any comparison? I mean, they are more regular than what we see in AGN, but the interpretation on the disk is similar. So,
for now, the only thing I tried, it was like when I ran the code, I started from 10 solar masses to reproduce from the literature, if I'm getting the same one, and then I moved to higher black hole masses. But I think it would be nice, there is, for example, this alpha X, this ratio between X-rays and UV, to check simultaneously what's going on for the smaller black hole masses and for big one to check it, because there are a few papers which are suggesting that it can be the same phenomena. Yes. But it was not done yet for big sample. It was, I don't know, maximum 5 sources or something. Because also for 10 to 7, the time scales will be, we have to wait a bit longer for this to change. But it would be nice to collect a bigger sample to compare with smaller black hole masses.
We have no questions from our audience from Zoom. So we have no questions. We can thank the speaker again.